Right, students, today I'm going to show you how to work out the structures of a few molecules using NMR spectra, given the molecular formula of the molecule, as well as the integration of the different signals in your spectrum. So I'm going to try to do at least 3 to 4 examples in this short video to show you how to use the information from an NMR spectrum and work out the structure of the molecule. So we're going to start by looking at the NMR spectrum, and the first thing we do is look at the chemical shifts of the resonances in your spectrum. And you'll see that this methyl group, or this resonance, which is a triplet here, is in the methyl region of the spectrum. And since it's in the methyl region of the spectrum, it probably means that there's a methyl group present here. This integrating to 3 protons also helps to indicate that a methyl group is at this position. Now the fact that it is a triplet indicates that this group is bonded adjacent to a CH2 group using the n+1 rule. So the n+1 rule states that if a molecule is a triplet, it becomes a triplet because there are 2 neighboring protons. 2 + 1 = 3, and therefore it is a triplet. This CH2 group that is somewhere in the other resonances, being adjacent to the CH3, now if there were nothing next to it, would mean that this CH2, when I say nothing next to it, I mean there's no proton groups adjacent to this carbon. So if there are no proton groups adjacent to this carbon other than the CH3, this CH2 would be a triplet. This CH2 would be a quartet because of the n+1 rule. 3 + 1 = 4. And if I look at my region of the spectrum at 2.5, I see a quartet. So it's highly likely that this is the CH2 in this simple spectrum. The integration also integrates to 2, meaning that's a CH2 group. The fact that it's a quartet means it's next to a CH3. So if I look at this CH2-CH3 group on its own, if it were next to something else, now remember there are 4 bonds to each carbon. There's 3 hydrogens and a carbon, so that's 4 around this carbon, 2 hydrogens, a carbon on that side, and something on this side, which would make it 4. So that CH2 and that CH3 would give us a splitting pattern of a triplet and a quartet if there are no other protonated groups attached to this carbon. If I look at my NMR spectrum, there's another singlet here, which means that this group has no adjacent or no carbons adjacent to it with protons on it, no protonated carbons on it. So I could now assume that's a CH3 because of the integration to 3 protons. As I said, there are no protonated groups next to it. The next thing I'm going to do is look at my molecular formula, and I'll see that the 8 protons, or the 8 hydrogens in the molecular formula, are all accounted for. 3, 6, 7, 8. The carbon atoms are not. There are 4 carbon atoms, but just 3 carbon atoms in the groups that I have. There's also an extra oxygen. So there's an extra carbon and an oxygen that I need to account for. And I need to incorporate that in my molecule. If I make that a carbonyl group, I need to put something on this side of the molecule that has no protons that would fit perfectly with that group. And the last thing to put into my structure is my remaining CH3 group, which is the singlet. And I have a structure. Let's see if this structure now agrees with this molecular formula. I have 3, 4, 5, 6, 7, 8 hydrogens, 8 hydrogens, 1, 2, 3, 4 carbons, and an oxygen atom. There's an oxygen atom. So the molecular formula here is C4H8O. So that shows you how to solve a simple molecule like this from NMR spectrum. The next molecule that I have is something along the same lines with the molecular formula of C5H10O2. And if I look at my spectrum, I see the same types of patterns that I saw in the previous example. I look at the aromatic region first, so I'll look at the aliphatic region first, and I see that in the methyl region of the spectrum, there are 2 methyl groups. Now, these methyl groups I'm writing in here because they're in the methyl region of the spectrum, and they integrate to 3 protons. So I know that that's possibly a CH3, and that's possibly another CH3. I also know that these 2 CH3 groups are not equivalent. So they must be in different environments and next to something else. So each group must be next to different substituents. The molecule then I know will be unsymmetrical. I then look at each of these, and each of these groups, like we did previously, must be next to a CH2, the reason being is that they each are triplets, and something will split them into a triplet, and that's a CH2. So 2 hydrogens, the n+1 rule will mean that this is a triplet. 2 + 1, that means that this is a triplet. So these 2 methyl groups will be triplet. It's very important to note that the CH2 group itself will not be a triplet, but the methyl group adjacent to the CH2 group will be a triplet. And that's what we see here and there for that and for that. And then I look at the rest of my spectrum, and these 2 CH groups I find in the other regions of the spectrum. I find one here at 2.2, and I find one here at about 4.1 or so. And this indicates that these 2 CH2 groups, I can write them in here now because, for one, they integrate to 2 protons, and secondly, I probably can assume that these are these CH2 groups here, because if they were next to the CH3s, they would be quartets, which means that there's nothing else adjacent to this carbon, no protonated group adjacent to that carbon. So this is next to a non-protonated group, and that's next to a non-protonated group. That would give me a quartet for one, and a quartet for the other. 3 + 1 = 4, 3 + 1 = 4. I then go back to my molecular formula, and again I see that I have accounted for all 10 of the protons in the molecule. 3, 6, 7, 8, 9, 10 protons, and I've accounted for 10 protons. I haven't accounted for all 5 carbon atoms. There are 1, 2, 3, 4 carbon atoms. I need 1 more carbon atom to be in my structure. I also need 1 more oxygen and another oxygen as well, because there's 2 oxygens that's left. So I need to find the structure that has this group in it, that group in it, that carbon, that oxygen, and that oxygen, which means putting these groups together in some sort of fashion. So if it were an ester group like I have here, there's something else to go on there and something else to go on there. And I have 2 other groups. And this makes perfect sense since one of the CH2 groups is very de-shielded around 4. So it makes perfect sense for that CH2 group to go next to this molecule. Oh, sorry, this atom, this oxygen atom here. So this one of the ethyl groups will go next to the oxygen, the other will go next to the carbonyl group, and the ethyl group, the CH2 that's adjacent to a carbonyl group, is normally found in the region of just after 2. A CH2 group directly bonded to oxygen is normally found in the region just after 4, around about 4. Which means that the structure of this molecule is this ester, and if I try to look at the molecular formula again, 5 carbons, 10 hydrogens, and 2 oxygens, I see 5 + 5, 10 hydrogens, 1, 2, 3, 4, 5 carbons, and 2 oxygens. So this structure matches this particular spectrum. Good, so I hope you enjoyed solving those two structures. I'll try to do another two in a following video.